So next we're going to talk about vertical stretches and shrinks. Here's our basic f of x equals the absolute value of x function. Stretches and shrinks occur vertically when we multiply the outside of the function by a value other than 1. If we multiply by a value where the absolute value is greater than 1, that is a stretch. And if we multiply by a value that is between 0 and 1, that is called a vertical shrink. So let's see what happens when we multiply by some numbers. Let's look at g of x equals the 2 times the absolute value of x. Now don't get confused because these are absolute values and the function we're using is absolute values. This is just saying that it doesn't matter if you're going up or down. We've already talked about what happens with a negative, where that actually causes that vertical flip. So if I multiply by 2, right, I will explain what I meant by that. G of x, right? So negative 2, negative 1, 0, 1, 2. I take the absolute value of 2, which is negative 2, which is 2, and multiply. That's 4, 2, 0, 2, 4. And so there is a vertical stretch. We call it a vertical stretch because you kind of think of it, if we were to pull up on it and it's stretching it up, it makes it a thinner function. When I was talking about that absolute value, just as a real quick aside, not really an aside, but to make sure you understand what I meant, if I were to take a function like h of x and call it negative 2 times the absolute value of x, now the negative part we know is going to cause that flip, but the 2 is also going to stretch it, right? So negative 2, negative 1, 0, 1, 2 is now going to be negative 4, negative 2, 0, negative 2, negative 4. And so it's still going to have that same stretch factor, right? Because the absolute value of negative 2 is 2, so it's still a stretch, but it's also a stretch and a flip. Those are just two separate transformations. So anyway, talking about the shrink now. So notice the vertical stretch caused it to be more narrow. If we were to take a function, we'll call it h of x again and make that 1/2 the absolute value of x. So negative 2, negative 1, 0, 1, 2. Absolute value of negative 2 is 2 times 1/2 is 1. 1/2, 0, 1/2, 1. So this becomes a wider function. Now, one thing that I want you to notice, this is where that 1, 1 point that we were talking about that's in all those functions comes into play. If we look at that 1 function, that 1 point, right? Notice that that 2 is the same as that 2. By going over 1, whatever you have to go up or down, that is the stretch or shrink factor. And if you go over 1 from wherever you start, and in this case we're starting at the origin, but if we had shifted it, then it still always go over 1 from that starting point, and then whatever distance you have to travel up or down to get to the function, that tells you the number that goes out in front. And we'll look at several of those so that you can see exactly what I'm talking about. But this is where normally we have that 1, 1 point, but because we multiplied by 2, that's where that 2 comes from. Because we multiplied by 1/2, that's where that 1/2 comes from. And we will see how to put all this together in the next couple of minutes. When we talk about horizontal stretches and shrinks, as has been the case with everything else we've seen, the horizontal works in the opposite direction as what we would normally think. So let's look at our absolute value function. Now, what we're going to notice here is if we multiply by 2, so let's say we take x, and then we'll call g of x will be the absolute value of 2 to the x. What's going to happen there, we plug in -2, -1, 0, 1, 2. This is going to look just like it did when we did a vertical stretch. All right, this is going to be the exact same function as when we did that vertical stretch. The only difference is now we're thinking about it as a horizontal shrink. So it's not going out as far. So the fact that it's taller vertically means that it's shrunk horizontally. So a horizontal shrink is the same thing as a vertical stretch, and vice versa. If we were to look at the function h of x equals the absolute value of 1/2 x, we could just as easily move that 1/2 to the outside, but -2, -1, 0, 1, 2, we take half of that value every time, and now it's just a flatter version of the function. But again, that horizontal stretch is the same thing as a vertical shrink and vice versa. But notice, right, stretching occurs horizontally, we call it a stretch, when we multiply by a number less than 1, or in between 0 and 1. And the horizontal shrink occurs when we multiply by larger numbers. Now, that's everything that there is to know about about transformations. And individually, each one of these transformations can be pretty simple. It doesn't really get difficult until you start doing all the different transformations in the same problem. So you're going to look at your notes and you see that there's some guidelines, some general patterns among transformations. A value affecting the input is horizontal. Values affecting the output is vertical. In other words, inside the parentheses is horizontal, outside the parentheses is vertical. We've seen that in every example that we've done. Vertical transformations work forward the exact way that you would think they should. Horizontal transformations have a tendency to have the opposite effect that you would suspect. So we're going to talk about the order that you do these transformations. And we're going to use RST. ARA. This is ARA. RST. So we're going to reflect. We're going to stretch and shrink. And we're going to translate. And remember when we did that shifting at the end, I said, all right, let's call it translate so that we can use that T, right? That's why I said, all right, let's call it translate. So reflect, stretch and shrink, and then translate. That is the order that you do things when we are working with multiple transformations in the same problem. And we'll look at some examples as far as what I mean by that. All right, so example 1 on your notes is basically what we've already done, just explaining each one of those transformations individually. If you look through your notes, you do see an example of each and every one of those. So the only ones that I'm going to do in example 1 are the ones that are at the very bottom. So here we are looking at a function that has been transformed in multiple ways. We can see that it has been shifted, it has been flipped, it has been stretched. So the question is, what exactly is going on with this function? So we're going to go RST as we look at this. And we're going to end up graphing it, but RST. So the first thing, has it been reflected in any way? And we look at that. Let's color code this because, you know, I love color coding. So R, we are looking for reflection, all right? This -2 right here on the outside shows us the reflection that we've got. Remember, if it happens outside of the function, so out here, that tells us that it is a vertical reflection. We also can call that reflection, right, about the horizontal line because it flips vertically, so it's reflection about x-axis. In other words, it used to open up, now it's going to open down. Next we go S. Is there a stretch or a shrink? So this time, we are looking at the 2 that is there. Again, it is on the outside, so it is a vertical. On the outside, vertical, a large number means that we have a stretch. So vertical stretch, factor 2. And then finally, we look at any transformations that occur. So our T, that is for transformations movement. This 2 inside, and we have a -3 on the outside. So we are going to move left 2. And remember, that's this way. Even though it's plus, that goes the opposite. And then down 3. So these are the different transformations that are being applied to this function. Now, when we go to graph it, what happens? Now, even though this is the order that they are applied, and when you do problems and when you're taking your test, it's going to say what order. This is the order you need to apply them. It's not necessarily the order that you use them in when we graph. Okay? So we're going to go ahead and try and graph this thing. And we're going to work with the T first. Where is this new function centered? Where does that V happen? Right? Remember, our regular old f of x equals the absolute value of x. It looks like this. And it's at 0, 0. Right? So that's our parent function. Right? That's what we're going to refer to. Now, we come over here and say, all right, where is the new one going to be? Where does this V actually happen? Now, this left 2, down 3 idea tells us where this point right here on our new function is going to occur. So if I go left 2, down 3, there is the point that my function is going to be centered around. Now, vertical reflection. That means instead, because it has a vertical reflection, instead of going up, we're going to come down, and we're going to stretch by a factor of 2. Over 1, down 2. Right? That's where that idea of having the point 1, 1 normally, we start where we're at, and notice, we reflected 2. So instead of going up 2, it's a reflection. We went over 1, down 2. That's this number right here. On the other, we go over 1 the other way, down 2. Because it's a V, connect the dots. There's our graph. We have taken care of the vertical reflection. It's moving down, stretched by a factor of 2. Because we went over 1, down 2, and we have moved it from where it originally started, left 2, down 3.